Okay, so today we're going to talk about exponential growth. So this might be a review, but if not, it's just like any other graph, right? There's going to be patterns, you're going to translate it, you can graph it, but here we go. So if the variable is not in the exponent, then it is not an exponential function, right? So if you ever need a hint, right, we have exponent and we have x, right? And we have our exponent right here is our x. So sometimes people forget, but this is an exponential function. And we have a few vocab terms. We have our initial value, which is a. And then we have our growth decay factor, which is the thing inside the parentheses that is being raised to the power. Oh, I could put that in a little note, right? Inside parentheses being raised to the power x. Okay, so we have two really important conditions. A is not allowed to be 0. If a is 0, then the entire function becomes 0, right?
Yeah.
If a is 0, the whole thing is 0, right? So then we just have y equals 0, which isn't an exponential. This is a linear, right?
It's like trying to divide by 0. You just get nothing out of it.
Yeah. Okay, condition 2, the base is a positive number other than 1. Okay, so this is for growth, right? It's positive number, that's growth. In the next lesson, we'll talk about decay. So sometimes this could be negative or less than 1, but we'll talk about that later. Okay, so now it's more just like determining, like, are we exponential or are we not exponential? So identify if the following functions are exponential. If they are, state the initial value and the growth decay factor. If they're not, explain why. So let's start with A. So if we look here, well, this one is actually easier to start with the growth decay factor. So we're looking, right, what is being taken to the x power? We have 2, right? Our growth decay factor is 2. And then you can't tell, this one's a little tricky, but our a is actually 1, right? We could rewrite this as 1 times 2 to the x. And now it's easier to see that our a is 1. So since we have an a that's not 0 and our b is not, something other than 1, then we can say, yes, it is exponential. Okay, if we look here at this example, we don't have an x in the exponent at all, right? We have an x in the base and it's being risen to the second power. So if we were to rewrite this using exponential rules, we have 4 over x squared. That's not exponential. It doesn't look anything close to exponential. It might sort of trick you because over here, right, it sort of looks like it's following the exponential form. But you can't have b as a variable and, right, there's a number up there, not an x. So this one, no. All right, we don't have an a, we don't have a b, right? No x in the exponent. All right, next one. Is it exponential? So we have our a, which is -3. We have our b, nice, 2.6. So is it exponential? Yes. Even though this a is negative, it's still, right, there's no rule for that. It just needed to be not 0. All right, 10 times 6 to the -x. So this one's a little tricky. We're going to rewrite this. So we have 10 over, or 10 times 1 over 6 to the x. So that's how you could write that. You could also write it as 10 over 6 to the x. So this one's really, really tricky, but if we look, we do have an x in the exponent. So you actually can rewrite this as f of x equals 10 1/6 x. So our a is 10, and our b is 1/6. And it is a positive number. So is it exponential? Yes. This one's much trickier. It's tricky to be able to turn this into this, but it's a good skill to have. So make sure you feel comfortable with your exponent rules. And you can also graph it. Once we start going into the graphing section, you can see, like, once you graph it, you can tell it's exponential. All right, and then we finally have 2 times 5 to the e. So if we look here, this isn't a variable. It's a number. If you remember from previous notes that we've talked about, it's an irrational number. But regardless, it's not x, so no. Okay, right, so we don't have an A or B. Okay, so let's go to linear versus exponential. So we have 2x and then 2 to the x. So they look similar, but they're not. Make sure when you're writing stuff on your paper that you're very careful, right? I'm going to write this on the side because it's important. Make sure you write carefully so I don't confuse 2x and 2 to the x, right? If a teacher's grading your paper, if an AP teacher is grading your paper, like, you don't want them to be confused. You want to be very careful. Okay, so if we're going to graph these, we have 2x. So we should know that with here, our slope is 2, our y-intercept is 0. So we start with our y-intercept, we do our rise over run. This is our graph of 2x. And then for 2 to the x, it's actually going to look a little different. It's going to look more like this. So it's similar in that it goes up, but still not quite the same. Oh, actually, I made that point wrong. So you don't have to draw the exact graph, you could just sort of sketch it. But as long as you get that, like, curvy appearance. All right, so in our exponential growth functions, what do we use for b? Green. If b is greater than 1, then the graph will grow away from the asymptote as we move left to right. So I'm going to be more specific. This is the horizontal asymptote. So the x-axis is a horizontal asymptote of the graph. An asymptote is an imaginary line a graph approaches more and more closely. So asymptote is a vocab word. So you should know it or will know it. But let's take a look at this graph. So we have so we have our point here at 0, and then it goes up and goes up. So this is just the pattern. We don't need to, like, give exact values. This is as long as b is greater than 0, right? This is growth, right? Our domain here, right, what x values this could be, is all real numbers. You can also write that with a little double-lined R. And then our range is y is greater than 0, right? It doesn't ever hit below that. We could also write that as open parentheses, 0, infinity, close parentheses. Let me see what the back side. Okay, so, right, another way of thinking about this is exponential growth grows away from the x-axis, right? So we can say, like, right, our x and our x, and we're growing away, right? So exponential growth grows away, right? It's like a baby bird leaving its nest, growing up. Okay. So now we need to think about the difference between exponential growth. So are the following graphs exponential growth functions? So let's just think right here. Right, we have our horizontal asymptotes. Usually asymptotes are with dotted lines. So let me actually make these dotted lines. Okay, so if we look, this is actually getting closer and closer to our x-axis, right? That horizontal asymptote. So this one is a no. It's getting closer to x-axis. This one, though, actually, no, this one's the same thing, right? This x-axis, it's getting closer to. So this is a no. Right here, we're not getting closer to the x-axis. We're getting further away. Over here, we're getting closer to -2. Actually, let me check this. Okay, actually, I got confused. This one, we want to think from left to right, right? So check growth from left to right. All right. Okay, so let's start this over. This is tricky. In the future, you'll be able to see by the equations, but we obviously want to be able to tell by the graph. Okay, so if we're going from left to right, we could see we're approaching a horizontal asymptote. So this is going to be a decay function. Right? This one, we're going left to right, and it's away from our horizontal asymptote. Right, so I'm going to put over here, horizontal asymptote equals, or HA equals horizontal asymptote, horizontal line a graph approaches. Just a reminder. Okay, so this is growth. Right, if we're going from left to right, it's not getting closer to any horizontal line, so this is also growth. And then we're going left to right. We can see that it's getting closer to this right here, +2, right? So I'm going to put this over here. Getting closer to y equals 2, which is a horizontal asymptote. So let me change these dotted lines. Right, this is the horizontal asymptote here, and this is the horizontal asymptote here. So the trick is going left to right like a book, right? So this one's decay. Okay, so now we're going to graph it ourselves. So the trick with graphing, I'm going to write this in a bright big color, right? When graphing, if you're stuck, use X, Y table. Right? We can call that plug and chug. Okay, so what does that mean? We want to pick some easy values for ourselves to calculate, and we just make an XY table. So we're going to start with 0, 1, 2, 3. We can go all the way up to 3. So if we plug in 0, right, we get 1/2 times 2 to the 0. Anything to the 0 is 1, so we get 1/2 times 1, so this is just 1/2. If we plug in 1, we have 1/2 times 2 to the 1. So we have 1/2 times 2, which is just 1. 1/2 times 2 squared, so 1/2 times 4 is 2. And then 1/2 times 3, times 2 to the 3, that's 8. 8 divided by 2 is 4. So we have these points, and now we just got to graph them, right? Even if we see this and we're super confused and we don't remember, you can always make an XY table, because sometimes it's going to just help you understand the pattern, right? So we have 0, 1/2, 1, 1, 2, 2, 3, 4. And now we can see, okay, I know this pattern. I'm going to start connect the dots. It's going to get more and more steep. And then over here, it's going to get closer and closer to that horizontal asymptote. All right. So if we look at our domain is all real numbers. And our range, again, is y is greater than 0. So graphing is as simple as any other graph. You just plug and chug. You just got to be careful. You can use your calculator sometimes. Okay, for exponential functions that are in the form a times b to the x, the graph will go through 0a and 1ab and have an asymptote on the x-axis. So that's the line y equals 0. So these are just 2 points that will help you graph it first, right? So if we look over here at this example that we just did, right? So we had y equals 1/2 times 2 to the x. We had our a equal 1/2 and our b equal 2. So if we look, right, 0a, so 0, 1/2, we had that right there, right? And then we had 1a times b. Well, a times b is 2 times 1/2 is 1, so we had 1, 1, so we had that there, right? So this is like a pattern that you'll always see and will help you graph. Okay, so let's try some examples. So we have a equals 1/2, b equals 3, and then here we have a equals -1, b equals 2. So let's do our XY table. So we have 0a, and then we have 1a times b. So 1, 3 over 2, 1, -2, right? So that's the first point. And then let's just do the next one. 2, so we have 1/2 times 3 squared. That is 1/2 times 9, so we have 9 over 2. Or 4.5, 1.5, 0.5. This is just helpful for the graphing. And then here we have 2. So if we plug this in, right, we have -2 squared. So we do the exponent first and then the negative, right? 2 times 2 is 4, so -4. So let's start to graph this. So you have 0, 1/2, 1, 1.5, 2, 4.5. And we can start to see this graph. Ooh. And then here we have 0, -1, 1, -2, 2, -4, and we can see that it's the same graph, but it's like flipped. So our domain here, right, our x and y will just keep going forever in the negative x direction and the positive x direction. So our domain is all real numbers for both of these, and our range is y is greater than 0. And here our range is y is less than 0, right? Because y is never going to be positive. Okay, so just like our other functions in exponential growth, we are going to have translation. So translations just means like moving. Okay, so to graph the function above, identify points for the graph of y equals a times b to the x, and then translate the graph horizontally, left to right, by h units, and vertically up and down by k units. So pretty much what you want to do is, right, we'll do first step. 1, identify a, b, h, and k. 2, graph using just a and b. 3, translate. All right, so let's go over that right now. So we have a equals 2, b equals 3, h equals 1, and k equals -4 from this right here. So we're going to ignore the h and k, and we're going to just graph if we had y equals to 3 to the x, right? So let's do an xy table for that. So we have 0, 2, 1, 6, 2, 9 times 2 is 18. Okay, so we have 0, 2, 1, 6. Let's do a -1. So -1 would be 2 times 3 to the -1, so 2 times 1/3, so 2/3. So -1 is 2/3. So we can start to see the pattern of this graph, right? You can see the exponential function. Sometimes it's easier for me to turn the paper to get towards that horizontal asymptote. Okay, so we have this, and now we need to translate it. We need to translate it 1 unit to the left and 4 units down. So we're going to just take these points, right? We're going to go 1 over and then down. So 1, 1, 2, 3, 4. 1. This one's harder. 1, 2, 3, 4, but then a little below. And then here we have 1, 1, 2, 3, 4. And then, yeah, that's all we can graph. And then it approaches our new horizontal asymptote, which is x or y equals -4. 1, 2, 3, 4. Right? Everything moved down 4. Well, over 1, down 4. Okay, so our new so let's do our original domain and then our range. So our original. All right, so our original domain is all real numbers, and so is our new domain. But our range was y is greater than 0, and now our new range is y is greater than -4, because we transformed right, our horizontal asymptote down. Okay, so hopefully this is a good review. Remember, whenever you're stuck, just plug and chug, right? Make an XY table. For some of this unit, I'm going to ask you to not use your calculator. So you just want to get pretty good at exponential graphs. All right.